Here we're going to draw an exothermic potential energy graph. Potential energy. So that's opposed to kinetic energy, which is temperature. Potential energy, we're just going to mark using energy. Okay. And this could be in joules or kilojoules. Typically it is in kilojoules though. Okay. And then over here, this is going to be progressing, and the time, I'm not going to put units there, it varies based on what type of reaction you have. Some reactions are very slow, so you could have hours here. Some reactions are very fast, so you could have seconds here. So that's really just dependent on what's going on, but you should still know that it's energy versus time. Now, when we do exothermic, we have to remember that exothermic means that the heat exited, exothermic. And so in chemistry, it's a negative quantity. So that means the products are going to have less heat than the reactants. So our products can be down here, and our reactants would be up there. Okay? And again, when you draw these, you're drawing just an arbitrary graph situation. Okay? So if we start with our reactants having more, and then we draw the hump of activation energy, and then it's going to drop down to the product side because the reactants have more energy than the products. Because in the course of the reaction, that energy left or was exited the reaction or the system. Okay. So we have reactants here, products there. What is that hump again? The whole hump all the way to the origin line at 0, that whole hump is your activation complex. Because it takes a certain amount of reaction to get started. Even though this is exothermic and it's going to be dumping energy in there, it doesn't just start spontaneously. Okay, so if it's sitting on the counter, it's not just going to immediately have reactants drop and release. It still needs some energy to get going in that reaction. Okay, even if ultimately the change is negative. Okay, and that's that activation complex. Energy. Okay. Now, activation energy is the actual amount needed. Okay. So the energy of activation, EA, or activation energy, is the energy needed to get reaction started. And so if you were given a graph with numbers on it, you could actually just read the difference between how much the reactants were at and how much more energy that they needed to get started. Okay. And now enthalpy. Okay, we know we're going to have a negative value because it's exothermic. And we can measure that right off the graph as well, because that's the difference between the reactants and the products. The change, or delta, just like delta T. The triangle means delta or change in enthalpy, because H is measured in enthalpy. If we used E, it just gets confused with energy. So the change in enthalpy of this graph could be measured with the reactants and the products. And in this case, because it's exothermic, your delta H is going down or is negative. So reactants, products, activation energy, and this is all for the forward reaction because this is all going from left to right. If we were doing a reverse one, we would be going from right to left.